He has fever, he is listless, and his pulse is rapid. But what's going on inside the child's body? Germs, shown here as black hexagons, have infected his body through the bloodstream. The germs are repelling these amoeba white cells whose work it is to remove foreign materials from his blood. The white cells cannot dispose of them. But under stimulus of the germs, tiny particles called antibodies are being produced and poured into his bloodstream. The antibodies attach themselves to the germs and so change the germs that the white cells can engulf them. At first, the germs increase faster than the antibodies. If this continues, the patient gets steadily worse and may even die. Usually, however, as in this case, antibodies are produced faster than they are used up, and it becomes only a matter of time until the germs are all disposed of and the patient recovers. What's more, he now has a surplus of antibodies that will aid him to resist future attacks of the same disease. And so this child has what we call active immunity because he has developed his own antibodies. He has acquired this active immunity by actually having the disease. Fortunately, there's a safer way to get immunity. This is through vaccination. In vaccination, a substance called a vaccine is introduced into the body. The body responds by developing antibodies, just as in the case of an actual infectious disease. Unlike the disease, however, a vaccine does not endanger life. Let's study three types of vaccines. Calves are the source of smallpox vaccine. Cattle are subject to a weakened form of smallpox called cowpox. Large quantities of vaccine are produced by infecting healthy calves like this one with live cowpox virus. The virus multiplies rapidly, and by the 5th day, crusts have formed on the skin wherever the calf was infected. These crusts are collected. They contain the live germs which will serve as vaccine for human beings. Glycerin is added as a preservative and to provide a vaccine in fluid form. From this mixture, individual doses of the vaccine are prepared. The vaccine may be supplied in a capillary tube like this and applied directly to the skin from the tube. In this disease, the antibodies dispose of the germs, probably without the help of white cells. The child is safe from smallpox for several years. Another type of virus vaccine is used to protect against poliomyelitis. Here, a second type of vaccine is being made. Pneumococci, the germs that cause lobar pneumonia, are being used. For this vaccine, dead germs are needed because there is no weakened form of pneumococci as there is of smallpox virus. The live germs are killed with chemicals or with heat, as in this case. Now let's see how this vaccine, made from dead germs, works when injected into a live animal. The effect would be the same in a human patient. In the rabbit's bloodstream, the dead germs, shown as pairs of ovals, stimulate the formation of antibodies. As additional injections are given, more and more antibodies form and combine with the germs which are then removed by the white cells. This rabbit has now developed active immunity to pneumococcus infections. Now let's take a sample of this blood. The antibodies in the blood of this immune rabbit will attack pneumococci germs wherever they encounter them. After standing a few hours, the blood clots and a serum containing the antibodies separate. When a few drops of this serum are added to a culture of pneumococci, the antibodies come in contact with the germs. Clumps of germs and antibodies settle to the bottom. This is called agglutination. Now let's see how the same serum acts in the case of a rabbit already stricken with a pneumococcus infection. First, the serum is injected into the rabbit's bloodstream. Soon, the antibodies in the acquired serum begin helping the white cells dispose of the germs. In about 2 days, the rabbit recovers. He has passive immunity. Passive because he did not develop his own antibodies, but acquired them from the serum of another rabbit. A third type of vaccine involves the use of poison given off by certain kinds of bacteria. In diphtheria, illness is produced by this poison or toxin. The toxin is first separated from the bacteria. Next, formaldehyde is added to the toxin. Formaldehyde counteracts the poison, but does not destroy its ability to stimulate the production of antibodies. The resulting vaccine is called diphtheria toxoid. The toxoid is packaged, ready for use. It is safe even for tiny babies, and doctors usually recommend vaccinating children against diphtheria before they are 1 year old. When a child is given this injection, the toxoid stimulates the production of antibodies. These antibodies are effective against diphtheria toxin. After an interval of time, a second dose of toxoid should be given. This is called a booster dose. If this is done, the child will usually be immune to diphtheria throughout childhood and need not fear the disease, even though it is right next door. Techniques for controlling infectious diseases have been developed primarily through the work of scientists whose painstaking search for new knowledge and improved methods is never-ending. Animals, too, play an important role in the experimental development and in the production of vaccines. Vaccines against the diseases we have studied, and against many others, including typhoid, tetanus, cholera, typhus, and plague. Commercial laboratories make possible the large-scale production of vaccines that meet required standards. Finally, the campaign against infectious disease can succeed only if the public cooperates. Most important of all is vaccination in the early years of life. Many infectious diseases can be brought completely under control when vaccination against them is practiced universally.